at incidents, you'll see that there's quite a lot of incidents from the US. That's not because the US has a bad safety record. The reason is the US does have a large population of older pipelines, and therefore things happen in the US that possibly haven't yet happened elsewhere, certainly in the UK and Europe. So we have to learn from what happens in the US. The other reason, which is a very important reason, is that the US has got a very good reporting system for pipeline incidents. And I think any of you who've looked at the US regulator websites will see that they have a lot of information on them. So a lot of information means a lot of potential for learning. So just to give you a feel for this, we're going to be looking at incidents, basically gas transmission and hazardous liquid incidents. And if you look at the populations of pipelines in the US has got approximately over three times the population of similar pipelines in Europe. It may actually be higher than that because I've just taken gas transmission pipelines. The US breaks gas pipelines down into gathering lines and distribution lines also, so it depends on the pressure rate. And there's more than 20 times the population that's available in the UK. It's important for you to remember that, because when I talk about standards and codes, I'm going to talk very much from a UK perspective. Okay, so you could take the view, well, is the UK the most informed in this area, and what's it doing to make sure it's informed? In terms of hazardous liquid, the USA has got approximately 9 times the population that's available in Europe, and about 47 times the population in the UK. I don't know whether any of you have checked. I have asked for the notes of these lectures to be put on Blackboard. Have you got them? Great. Okay, that's fine. Okay, the causes of pipeline failure. And we're going to look at some fairly tight definitions of causes. We need good definitions of causes, because otherwise every time you go into a database you'll just simply have this incident occurred on such and such a date and this is what happened. That's not very useful if you're trying to pull together statistics in particular to apply in risk assessment. So the main causes of pipeline failure are generally categorized as material, fabrication or construction defects, external interference, either accidental or intentional, although there is a problem with intentional external interference, which we'll consider a bit later on. Corrosion, which is very, very important for, obviously, for any kind of high pressure pipeline. And any of you who've got an interest in corrosion, I'm sure you'll end up with a very good and lucrative career, because corrosion issues are very important, particularly because in most areas pipeline population is aging. Natural causes, ground movement and flooding in particular, are very important, because any kind of movement of the ground, disturbance of the ground, has the potential to apply very high loads on the pipeline and therefore cause failure. And then incorrect operation, which is generally associated with problems with procedures or operator errors. Most pipeline databases also include a category called other or unknown, which is generally a catch-all for anything else that's happened that you can't easily categorize. Covers a range of different causes, and most databases do record very well accidentally external interference, but not intentional external interference. And that's a problem, because intentional external interference is a big issue at the moment. Right, in terms of statistics, I've taken these from the UCOPA, which is the UK database. There you can see the breakdown of various failure modes, but very importantly, you can see the breakdown of ruptures. When you are doing any kind of risk assessment, ruptures will be the most significant failure mode. And what you can see there is the ruptures are caused by external interference or ground movement. Right, I'm not going to spend a lot of time on that one. It's just to show the slight difference in reporting between the USA and Europe. Right, so failure rates. Failure rates are basically reported according to the damage cause, so which is the cause which has resulted in either a leak or a rupture. And they're obtained from operational databases, right? If you're going to do risk assessment, you must have a good reference source for your failure rate, and therefore you've got to use a recognized database. The databases, sometimes you can use predictive models. The predictive models will always be related back to operational databases in one way or another. And the failure rate is generally given in kilometre years of operation or numbers of failures in X years of operation. When you're doing risk assessment, the failure rate that you derive from the databases needs to be specifically applied to the pipeline that you are considering. And in norm, what you would do is you'd look at all of the failure causes, damage causes, and you would consider, could those damage causes apply to this pipeline? If there's a justification for not applying them, then you can remove them from your failure rate. Okay, external interference is a very aggressive form of damage, mainly because it often produces combinations of gouges, which is where machine tools have removed material, and dents, which cause very significant stress concentrations, and in some cases, depending on the pipeline wall thickness, they will cause immediate penetration. One of the things that's important as I go through these, please pay attention to the kind of failures that occur for different substances, in particular gas versus liquid. Okay, this is a failure which occurred in a gas pipeline, which had actually been tested to a high level hydro test, and it failed while it was being gassed up. Okay, so it was designed for 70 bar or 69 bar operation, and it actually failed at 56 bar during gassing up. And what you can see here is the pipeline has ruptured, and ruptures in gas pipelines look very different to ruptures in liquid lines, and you'll see that as we go through. But in this case, the rupture has arrested, which means that the material properties were okay. They prevented a propagating fracture. And the reason the pipeline failed was it was damaged by construction machinery after the test and before commissioning. Okay. And as a result of this failure, certainly in the UK, the construction procedures and management procedures for construction sites were changed to make sure that once a pipeline has been tested, whether it's been gassed up or not, it must be treated as an operating pipeline, and all restrictions across the way leave must apply. Right, I've put this particular incident in because it's still a reference incident for pipeline quantified risk assessment. This was actually, it's an old incident that occurred in the USA, and it's on a gasoline pipeline which was struck by basically a digger bucket. And what happened here is the rapidly vaporizing gasoline created a fog-like atmosphere, right? So it was a hole in the pipeline, not a rupture. It was a hole, but because the pipeline was under high pressure, basically the gasoline was emitted as a spray, which created a fog, which then created a huge fire. And so this is still a reference incident for QRA of gasoline pipeline. So there you can see the fire that occurred, and here you can see the hole that was created by the digger bucket. So you don't, certainly with liquid pipelines, you don't have to have a rupture to have a very serious consequence. This is an example which this sort of event has become more common in recent years. Basically what we have here is a distribution pipeline has been installed right next to a transmission pipeline, and the transmission pipeline was actually reduced in pressure while the work was going on, but it was damaged during the work. It was damaged by a molding tool, and it failed when it was being gassed up again, and you can see the rupture which occurred. So use of no-dig technology in pipeline construction is a source of damage to existing pipelines, so you need to be very careful that you do understand where the in particular things like molds are being deployed. This incident is an important incident because it's one of the two incidents which actually changed the safety legislation in the US. The change in legislation actually occurred in 2000. This is a gasoline pipeline, and you can see from the photograph there, there was a massive fire. The release occurred basically in a water creek, and so it flowed away with the water. It was on top of the water. It found an ignition source, so it burnt all the way back to the source. Now that is a picture of a typical rupture in a liquid pipeline. So you can see it looks very different to a gas pipeline. Basically, ruptures are defects which are not stable. So during the failure event, the defect will grow. So you can see this has grown, but it's very quickly ringed off and stopped. And that's because in liquid pipelines, as soon as you have any sort of damage or release, the pressure drops very quickly. That doesn't happen, of course, in gas pipelines. Now, this was taken very seriously by the American regulator because basically the pipeline that was damaged was very close to a water pipeline, and the local water company had had several goes at their pipeline, and they damaged this pipeline every time. And the damage was evident on the inline inspection for the pipeline, but the operator didn't know how to interpret the damage and didn't actually dedicate any effort or pay any money to get experts to assess it. So the pipeline accumulated quite a lot of damage, which you can see on these photographs. And then the combining event, you often find with serious incidents there's more than one cause of failure. The combining event here was that the pipeline operator had just installed a new SCADA system, and the control room staff weren't totally familiar with how it operated, and so there was a pressure surge in the pipeline, and it was that pressure surge which actually caused the failure. Right, this failure is of a gas pipeline which occurred in Gislingham in Belgium in 2004. The pipeline that failed is this one here, and you can see in the background that there was another pipeline which remained operational throughout the incident. It was a very large pipeline, and what had happened was there was construction work going on above it. It was running through an industrial park, and the park had been extended, and there was a big car park being built over the pipeline. And the pipeline was damaged as a result of the work, and you can see there was a very large fire, and there was a lot of fatalities and injuries. The injuries that occurred most of the injuries that occurred in this were because the fire was so large that it actually closed the road. The road, it was an industrial area, so people were travelling to work. This happened at about between 8 and 9 in the morning. People were travelling to work, and they got stuck in their cars, and there was a lot of basically injuries as a result of exposure to thermal radiation. What caused the damage in this case was massive external interference damage to the pipeline, and it was probably caused by a machine which looked like this, probably this one here. And again, one of the issues here was the construction company that had been brought in to do the land conditioning and to lay the surface of the car park had not been informed of the pipeline. Okay, so it was a typical loss of communication. This is an example which I've included this because it was actually used by the Health and Safety Executive in the UK to draw attention to pipeline operators in the UK as to the kind of things that could go wrong if your records were not very good. This was actually a gasoline pipeline which was running through a paved area, and the contractors were using construction diagrams that they'd been, route diagrams that they'd been given, which didn't account for the fact that the original pipeline had been routed around a large oak tree which had subsequently been removed. It had been removed above ground but not below ground, so the pipeline route was not where the contractors expected it to be, and so the pipeline was punctured during the work. Right, we'll go on and have a look at some corrosion failures now. The worst corrosion failure that has probably ever happened occurred in 1989 in the Ural Mountains in Russia. This particular pipeline, it was a natural gas liquids pipeline. Natural gas liquids is a horrible hazardous substance if it releases because it's dense, so it releases as a cloud, but it stays at ground level, so it can spread out and become incredibly hazardous. This was a very bad accident because essentially the area was completely and utterly uninhabited with the exception of a train line, and it was the train passing loaded with passengers that actually caused the ignition of this, so there was lots of fatalities and injuries. And that's one of the only pictures that I've ever been able to find of this incident. You can see here the wreckage of the train, and you can see the massive burnt area which occurred. The other thing, of course, was this was miles from anywhere, so once it had happened, it took a long time for the emergency services to actually get there. The other significant learning point was that the operator was under pressure to keep this pipeline operating. It was a very long pipeline, and it was feeding some sort of industrial process at the other end. And the operator was having trouble keeping the pressure up, so they kept increasing the pressure. And of course, the reason they were having problems keeping the pressure up was it was leaking, which of course is a mistake which is quite common and easy to see how it gets made when the operators are very remote from the location of the pipeline. Right, this is the one which I've included because, again, it's a pipeline rupture. You can see a typical liquid rupture there, and this particular one, again, it occurred after a pressure surge, but it actually created massive environmental rather than safety issues. This is an interesting one. The point I really wanted to you to put on here, first of all, it's microbial corrosion, and look at the state of the coating on the pipeline. So obviously microbial corrosion was possible because of the ground conditions there, but the coating really was in a very bad condition, and it had been allowed to deteriorate, so microbial corrosion occurred. Again, it occurred as a rupture, and what happened here was there was a series of corrosion pits under the which were following the wrapping of the coating, and so they were all in nice neat little lines which then could very easily join up once they got to a certain size. This is the other incident which contributed to the change in the US safety legislation. This is the Carlsbad incident, natural gas pipeline which failed by internal corrosion. It was a massive pipeline rupture. Again, it occurred in the middle of, this was microbial corrosion. It occurred in the middle of nowhere, except it was quite close to the river where a family had gone on a fishing trip. So they were actually camping very close. So there were all fatalities as a result of this incident. And again, what happened here, and the reason why the regulator took this so seriously, was that the internal corrosion occurred because the gas that was being transported was actually, it contained fluids. And the operator knew it contained fluids, and their maintenance procedures required them to pig the pipeline and drain it at regular intervals. However, there'd been some ground movement, and so the level of the pipeline had shifted, and the low point where the drain actually was located was no longer the low point in the pipeline. So the operator hadn't actually gone through the draining and cleaning process. The liquids contained microbes, and the microbes caused very aggressive corrosion, which of course was along the strip in the bottom of the pipeline, so it occurred essentially as an axial groove, perfect defect conditions for a rupture. One of the issues in terms of corrosion which is causing a concern at the moment is external stress corrosion cracking. This causes major concern because the cracking occurs as basically tight populations of crack defects. They're often very short, but and they're not that deep, but they are very, very sharp, and because they occur over an area, it just completely reduces the strength of the pipeline in that area, and because they're sharp, they're essentially crack-like defects. So it's a very aggressive form of corrosion, which you can see there. This is an example of external general corrosion, which is actually quite unusual. You don't often get major serious incidents now, particularly now, due to external corrosion, simply because most pipelines are inline inspected, and so you would expect to pick up corrosion. This particular pipeline was basically through a very, very remote area, and obviously the scheduling of inspection hadn't been frequent enough, so it failed. It was in the middle of nowhere, so there was no safety consequences, but it was quite a critical supply pipeline, so it did cause a lot of supply disruption at the time. And the final one I've included for corrosion, again because this one was in the media for quite a long time, and BP took a major hit over this, because basically this particular pipeline, which was assets that they'd bought to extend their asset base in the Arctic, and basically there was no operating or maintenance procedures for these pipelines, so nobody took a great deal of notice of that until there was a major leak. Because it occurred in the Arctic, there was massive public reaction to that. This is an interesting one, because this particular failure, which occurred in 2008, was one of three pipelines which was coming out of a compressor station, and all three pipelines had been inspected by the operator by inline inspection, and for this particular pipeline the results had not been assessed at the time of the failure. However, the other two pipelines had been remediated. They knew there was a problem with the coating. The pipelines were fairly hot as they came out of the compressor station, and so they'd done work to remediate the coating on the other two pipelines. They actually thought this pipeline was not as serious, and then it failed. Basically, as soon as the compressor station was reinstated to its operating pressure, And the follow-up report was quite interesting because the operator very quickly put out a statement saying that it had been inline inspected and the tools hadn't identified the corrosion defect. The corrosion defect was actually between 50 and 70% wall thickness. And so basically any corrosion, extensive corrosion of that depth is going to fail through wall, and once it's failed through wall, it's going to rupture. And the interesting thing was the inline inspection tool had detected an anomaly, but they had classed it as a manufacturing defect because of the shape of the defect. And it was a smooth shape, so they didn't expect it to be corrosion, but it was. Right, now looking at material and construction defects, again, there's some interesting old ones here. This is an old one which I've included. Again, it's a natural gas liquids pipeline. The message here is if you've got one of these pipelines, you certainly make sure you look after it, because if they fail, they cause huge consequences. The failure causes in this case was the fracture had initiated in the cold work area of a dent and gouge in the pipe caused during construction. So obviously whatever inspection it had been subject to following construction had not been specifically detailed, and it did have a dent gouge combination, which often, because of the cold work to the material, has crack-like defects in it, and the cracks grew due to pressure cycling. So that's a picture of it. Again, you can see in this case, it's obviously because the fluid is pressurized and partially gaseous, it did rupture, but again, the rupture did stop. So the material properties were okay, they just hadn't been inspected thoroughly following construction. Right, this one is included because it's a seam weld defect. It's a rupture which occurred due to a fatigue crack in old ERW pipe. If any of you are studying materials and manufacturing as used in pipelines, you'll be aware that ERW pipe is well used today, but when it was first manufactured, the manufacturing process left extensive defects in the seam weld all the way down the pipeline. So again, it was very prone to failure. Any pipe which was subject to any kind of pressure cycling was a potential failure, and most pipes which used ERW, old ERW pipe, most of them have been quite significantly derated to prevent that sort of failure. Right, this one, again, I've put this introduced a major change in US pipeline specs. This was failure of seam weld due to fatigue, but it was quite an interesting failure. Again, you can see there the typical liquid rupture. That's obviously not the one I was thinking about, because either that or I've inadvertently deleted a slide. I apologise for that. The issue was the pipe had been transported for hundreds of miles on a train, and therefore it had been subject to vibration on the train, and that had caused very small crack-like indications to initiate in the seam weld, and then once it was in service, though they continued to grow by fatigue. And so the requirements for transporting pipes on as rail freight were significantly controlled following that failure. Right, this is the San Bruno pipeline, which failed in 2010. Again, it caused 8 fatalities and destroyed 38 homes. Quite an interesting historical issue, and I think there are a number of typical issues like this around the world. You can see that the area was quite built up when the failure occurred. So a lot of the infrastructure was destroyed. Now, when the pipeline was built, it was actually built in 1956, so it was well over 50 years old when it failed. And when it had been built, there had been absolutely nothing in that location. So it shows the fact that things happen around pipelines during their lives, which then significantly affect the risks that those pipelines pose to the surrounding people and infrastructure. So there was a lot of learning from this incident, which I won't go through in detail, but the key failure was to do with this. Basically, what happened at the time, it was practice when you were doing pipelines, you collected all the bits. You know, you would have to cut down lengths of pipe as you were constructing the pipeline, and you'd end up with bits of pipeline, which were then used to basically fabricate around difficult issues or changes in levels. So the section of pipe that failed had 6 short pipeline pups in it, all with mitre joints, and 5 of those pups were included in the rupture. So that quite clearly is going back to the quality of construction. The failure occurred at a flaw in the longitudinal weld of one of the section pipe, which grew over time. And when the failure was investigated, the seam weld that was in the pipe didn't actually meet the quality requirements which were in place in the 1950s. So it was quite bad. The pipeline couldn't be inline inspected. However, if it had been inline inspected, it's highly unlikely, as it was a gas pipeline, it's highly unlikely that any of the inspection tools used would have found the defect which failed. But the other interesting thing which came out later was that the pipeline was scheduled for replacement, and it failed 2 years before it was due to be replaced. So the operator knew that there was problems with that pipeline. And what had happened here was that the upstream installation on the pipeline was being maintained, and during the maintenance activities, the UPS system was inadvertently decommissioned, and what that meant was that the control valve received the wrong signal and immediately opened the pressure regulator up. So there was a pressure surge which occurred at the time. And there you can just see there was obviously a very detailed investigation which basically confirmed that the pipeline had been in place for more than 50 years. It didn't meet the quality control or welding standards at the time of its construction, so it certainly didn't meet ones that were in place in current days. The pressure had increased for the reasons that I explained, which weren't evident at the time. However, once the failure did occur, it took the operator 95 minutes to actually locate and operate the shut-off valves. So all of that time, the gas was being fed to the failure site. So I think if any of you follow these sort of things on the internet, you'll see that this legal case is still really going on. Right, ground movement. I mentioned the reason ground movement is important is because it can obviously apply massive loads to the pipeline. And this is an example of a pipeline which it didn't actually, the failure didn't result in a release of gas, but it did fail because of the curvature damage which occurred. What had happened here was the landowner knew that the pipeline was routed through his land, but he wanted to create a massive landfill site. So he excavated that, and he very carefully went and dumped all of the soil on the other side of the pipeline. The soil became unstable and it slipped, and it took the pipeline with him. So at the time when this happened, this pipeline was a critical supply pipeline for the southeast of England, and so they didn't actually want to decommission the pipeline. So what they did was they excavated it to remove the loading on the pipeline, and they reduced the pressure so that they could operate the pipeline over the winter and then repair it in the following year. And the reason they had to repair it was, if you look at this one, this is a different pipeline, but it shows you the problem. This is actually a pipeline that was excavated so that it didn't get, or supposedly wasn't going to receive any loading due to land subsidence, which was occurring because of mining underneath. And what happens here is, if you excavate too quickly, the pipeline moves quickly and it kinks. And the kink, of course, is a structural failure which you've got to repair. And that's what had happened to the first pipeline. It had a couple of kinks in it.
Was there monitoring that was set up for this pipeline or excavated?
Yes, yes. Basically, if you do something like that, you're into daily surveillance, and the surveillance would have to be walking surveillance. Okay. Yeah. Right. So again, these are just examples of ground movement. The background picture is, again, this particular pipeline didn't fail in terms of releasing any fluid. It was a gas pipeline, but you can see there was massive axial buckle occurred. That was a result of mining subsidence, and the inset at the top, you can see that there's a buckle on the pipeline there. So ground movement does have major potential to cause failure. This is an example of basically a pipeline that was routed through a very marshy area in the US, which failed. And the issue with liquid pipelines often is that the environmental consequences are absolutely huge. And you can see here there was massive problems here. The failure was quite interesting. This is often what happens with ground movement failures. The pipeline will wrinkle because of the movement that's been applied, and the wrinkle, depending on the size of it, can be very, very high stress, and therefore you get fracture at the wrinkle, and then that fracture, well, in this case it didn't have to grow very much to release massive amounts of crude oil, but obviously there is a potential for the fracture to grow. This was a ground movement failure which occurred in the UK, and what had happened here was the wayleave hadn't really been managed properly because the landowner had dumped stuff over the pipeline, and then when this was deemed to be intolerable, the operator went in and started clearing it, and because this was just material which had been dumped over the pipeline, it hadn't been consolidated, so it was unstable, and it slipped, and the pipeline, I don't know whether you can see, this is the pipeline here. You can see it was just pulled apart, which again is a typical failure for any severe ground movement. I did mention to you that there's a category called other, unknown. This was a major failure which occurred in the UK, and it's categorised as other because there were several things which contributed to it. The main issue was the pipeline had been modified so that the road under which it was crossing could be extended to become a motorway. The previous road crossing was constructed using a pipeline sleeve. Pipeline sleeves were at this stage no longer best practice. Best practice was to use thick wall pipe. So the pipeline had been modified on site, and thick wall pipe had been welded to the existing pipeline sleeve, which was forged. The pipeline material was line pipe material, so there was difference in chemistry. The weld procedure that had actually been used wasn't really adequate for that situation, and so there was hardness cracking that occurred, but it actually occurred in the forging because the chemistry of forged material is different and not as forgiving as the chemistry of line pipe material. So it actually failed in the existing crossing.
Sorry, question. How do you classify this kind of failures?
Well, this one is classified as other because the causes of the failure were, there was three main causes of the failure. One was it had been modified on site, and the backfill, which had been placed under the pipe following the machining and welding, was not properly consolidated, so basically the pipe wasn't properly supported. There was a lot of loading over the pipe once the road had been constructed over it, and then there was the problem with the weld procedure. So if you were asked what was the primary cause of the failure, you don't really know. So if you put it under the other category, then people who are looking at statistics to apply in risk assessments should always look at other and find out, okay, it's classed as other, but what happens, and could that happen on my pipeline? And if it could happen on your pipeline, then you must use the statistics. So that's why it's in other. Did that answer your question?
Yeah.
Okay. Right, this is another example of a pipeline subject to ground movement. In this case, the pipeline was actually routed through a landfill site. Landfill sites are a problem because they're very rarely properly consolidated. So they very often you will have a situation where any pipes going through a landfill site will at some stage become unsupported. And this example is an example of where local construction close to an existing pipeline actually caused the construction occurred on essentially sloped land, and it just wasn't controlled properly. The construction work caused a landslip, and the landslip failed the operating pipeline, which was in the vicinity. It did cause quite a lot of damage at the time. Right, let's just spend a little bit of time looking at external interference in third world countries. This is often different simply because pipelines in third world countries are often routed above ground. Okay, if they're above ground, they are obviously going to be more susceptible to damage, particularly if there's no attempt made to control access to the pipelines. And as you can see from these photographs, these are actually liquid pipelines, and there was, there's no attempt at all to stop the local people actually crossing them, going very close to them. If they can get very close to them, there is the possibility something may happen that could damage the pipeline and then cause major safety issues to the surrounding population. Also, even though they're above ground, they're often not in terribly good condition. You can see on this particular pipeline, the coating is in very poor condition. Also, in some areas of the third world, the construction practice that's applied may not be ideal, and often will occur in very close proximity to local communities. So the issue here is different standards and different safety regimes which apply that really need to be considered. Another big problem, particularly in locations like Nigeria, is organised crime, theft, spillage, or what is probably more distressing is pilfering. Often these pipelines which transport fuel are routed close to populations which are very poor, and therefore the temptation to actually pilfer fuel is high, but the consequences are dreadful. Now that issue, somebody's just lost. I think that was a pound coin. notes under the board if you want to retrieve it later.
That's a watch
The intentional external interference in Europe has become a big issue over the last 3 years. And liquid pipelines throughout Europe are being targeted. This is more to do with organised crime. But it is causing a massive upsurge in the damage statistics for liquid pipelines, which, obviously this sort of activity is against the law and it's illegal. The real controls that the operators have concentrated on historically in controlling external interference are accidental external interference. The pipelines are routed through third-party land. Third parties are entitled to work on the land, so there is a possibility you have an accident. Having an accident is completely different to having an intentional damage effect. So this is a big issue at the moment. The failure statistics are high. But at the moment, there's no real, other than going through criminal enforcement, there isn't a good way of preventing it. Right, so I won't go through each of these points in detail because they will be in the notes that you're going to get. But you can see, if you just scan that list, you can see that there are lots of learning points which you'd think, right, okay, that's a learning point. You should put it in a standard or a procedure or a specification and make sure that in future it can possibly be avoided. There is a requirement to look at coming up with adequate controls and standards for intentional external interference. The issues that are being considered at the moment are location of the pipeline. Do you need to put different controls on locations which are likely to be targeted for intentional external interference? Do you need to consider construction and installation standards in those locations? Government controls, what can you do to impose those? Land use controls and poverty are particularly important in locations in the third world where you can get high levels of pilferage, which could then cause absolutely disastrous accidents for the local community. Right, now, one thing I do want to draw your attention to in this, we've talked about a lot of incidents. In reality, there are only 2 failure modes of pipelines. Pipelines are very simple structures, so there's 2 failure modes. The first is a leak, and the key thing about a leak is it's small and it's stable. In other words, once you've got a through wall damage site, that damage site is not going to change or extend as a result of the release. In terms of a rupture, the defect is unstable and it will grow as the fluid is released. Typically, with liquid pipelines, you get limited growth and you get a typical fish mouth type opening, which is certainly big enough to get rid of huge amounts of pressurized liquid. In a gas, you will also get ruptures, but because gases will decompress as they actually pass through the defect, the decompression drives the defect, and so in gas pipelines you will get propagation that you won't get in liquid pipelines. Okay, there's a number of mitigations that you can apply. All of these will be covered to some extent in the pipeline codes. Pipeline operators, the concluding statement here, which we'll pick up in the next lecture. There's a responsibility under legislation for pipeline operators to actually identify what they need to do to mitigate damage. Incidents, in terms of standards, the standards that apply, incidents have got to be reviewed to identify any learning which has emerged in recent times. All of the learning from older incidents should be included in the standards that are used now. That's required to satisfy legal and code requirements, and also to demonstrate to any interested parties that the risk of the pipeline is as low as reasonably practicable. That last statement is particularly important in first world countries where people will have major reaction and complain about developments such as pipelines. I mean, I think if you think about the press in the US, they are forever dealing with people complaining about pipelines because they see that the risks of them associated with them are high, and therefore actually doing and applying actions to make sure you're controlling the risks is very, very important. Right now, I am curtailed in terms of time, so instead of being thoughtful and giving you a break, my experience of students, when you give them a break and you say, right, you can have a 5-minute break, 15 minutes later they're still not back. Right now I haven't got time for that today, so I do apologise for that. What we'll do is go straight on with the next lecture. Okay, so in this, having looked at a lot of accidents and seen that in a lot of cases the accidents, if there had been proper thinking, the accidents would have been avoided, or if there'd been more knowledge at the time, the accidents would have been avoided. So we're now going to think about, right, well, how do you capture that process? And you do it, first of all, through legislation. If you really want to control something, you've got to legislate. Leaving controls totally to operators and stakeholders is not really a good thing to do. So you've got to legislate. The legislation has got to require safety management, and then you must pick up the details that have got to be actually applied in the pipeline design, construction or operation. You've got to get those details into standards. If you don't, they'll be missed and they won't be applied. Okay, so why do we regulate pipelines? Well, pipelines are generally considered to be the safest way to transport hazardous substances, safest and most economic. And if you think about alternative transport regimes, you can see that. You know, if you have to transport a lot of hazardous liquid by road or rail, it's going to be much more dangerous, simply because of road and rail networks and what can go wrong on them. You may have to transport them by sea. Well, that's a different issue. You know, obviously you may not have access to pipelines in there, but transport by sea tends to be much bigger and better controlled. So in general, pipelines have got a good safety record, but as we've seen, there are serious accidents that have occurred, and once they've occurred, you get very significant volumes of material being released. You do get injuries and fatalities, and so you've got to apply controls to reduce the risk of So the key principles. Now I'm talking here really about legislation in the UK, but legislation in the UK is typical of legislation in Europe, and it's typical of legislation in the US. So the principles are not specific to the UK, and the key issue is the legislation has got to put duties on the operator for safe design and operation, safety management, control of major accidents, because with the best will in the world you might have a major accident, so if it does happen, how are you going to control it? And notification, very important. You've got to tell people what you're doing, where your pipeline is, and how it's being operated. And by telling people, we really mean you've got to tell the regulator, and then the regulator has got to tell all the local government organisations which are responsible for the land through which the pipeline is routing. And the bottom line is legislation has got to force operators to comply with codes and standards. So I'm not going to spend too long on this because I'm sure you'll do a lot in other lectures, other safety lectures. But in the UK, the Health and Safety at Work Act requires that risks to employees and others have got to be reduced so far as they are demonstrated to be as low as reasonably practicable. And this means they've got to be demonstrated to be a LARP. Reasonably practicable means you've got to assess the risk, and then you've got to consider what it's going to cost in terms of time, money and disruption to bring that risk down. If you can't bring it down far enough and the risk is too high, then you just can't do it. The legislation will stop you actually operating. If it's not so high that it's absolutely intolerable and you've done everything you can, provided you can demonstrate you've done everything you can, the legislation will allow you to operate. And so this reasonably practicable issue applies in all aspects of risk assessment in the UK, and I'm sure you'll be covering that in particular when you do quantified risk assessment as part of this this course. And essentially what this does is apply the Health and Safety Executive's framework for risk tolerability, which is well published in the UK, and this framework is actually applied in other parts of the world. Also, if you actually research this topic, you'd find that the risk levels that are talked about are fairly consistent. There's a fairly good, consistent agreement of them internationally. And essentially, what it means is that ideally you want your risk to be low enough so that it's broadly acceptable and you're safe to operate. However, once you start quantifying risk, you need actually to put a quantified level against that. And that means that the risk has got to be 1 times 10 to the minus 6 of a person becoming a fatality per year associated with the infrastructure you're talking about. Okay, so and obviously as soon as you start quantifying risk, things start to get emotive because people think, well, you know, the risk should be 0. And in the UK, an unacceptable risk is one which is 1 times 10 to the minus 3 to a worker, or 1 times 10 to the minus 4 to a member of the public. And the difference here is that if somebody is working associated with hazardous installations, they will have had training. There will be procedures that they'll have been told to follow, and there should be safety measures in place. Whereas for the public, if the public is subject to a major accident, there's none of those things, and you've just got to try and evacuate and control as best you can at the time when the accident's happened. If you're between these two levels, you're in the alert region, which basically means you should look to see if you can get the risk level down any further, and that means that you've got to look, evaluate what the difference in risk is compared to the time, cost and disruption that's going to be involved in applying it, and you can then apply the concept of gross disproportionation to that. Again, I think there's a little bit of discussion in the notes, but I know that this aspect is covered in more detail in other aspects of the course. The key thing, which is important for codes and standards, which is what I'm going to talk about really, is that when you're applying the ALARP principle to demonstrate that risk is as low as practicable, first of all, the application of that will assume that all controls are in place. That means you're complying with codes. And then what it goes on to say, the zone between the minimum and maximum risk has got to be evaluated. But this is the important thing. The demonstration of alarm starts with confirming good practice is being applied, and good practice means following pipeline codes and standards. This is what we mean by disproportionation. So basically what you've got to do is evaluate the level of risk reduction. So you do a risk analysis and calculate the risk without the risk reduction measures, then you calculate it with the risk reduction measures, and you use the reduction in risk as to basically proportion that to the costs. The benefits are expressed as costs per life saved, and normally if the disproportionation factor is less than or equal to 10, in other words, if the costs of applying the risk reduction are 10 times or less the value of lives that you might save, you've got to do it. If they're much greater than that, if they're greater than 10, you could come up with an argument to say it's disproportionate and therefore you're not going to do anything. However, you've got to remember, if you follow these arguments through, you have to be prepared to defend them in court. So it needs to be done robustly. Right, so we'll look at the principles of the UK pipeline legislation, which again, these are fairly broad principles, so if you looked at legislation in other parts of the world, you would see parallels. Basically, the key principles are, there's general duties which apply to all pipelines, and that means you've got to design, construct, operate, maintain and decommission them. You've got to do it properly, you've got to do it according to the codes. And then the additional duties for major accident hazard pipelines, which could cause major accidents if they fail. You've got to notify them, which means you've got to provide information to the regulator and local government organisations as to where the pipeline is and what pressure it's at, etc. You've got to prepare a major accident prevention document explaining how you're going to prevent accidents. You've got to have emergency procedures and arrangements in place. You've got to have those. And you've got to provide information to the local authorities in the UK or local government organisations so that they can use that information in their emergency plan, because in the event of any major accident, it will always be the emergency services who have responsibility for controlling and dealing with that accident. So just to summarise, the key principles for control of major accidents are notification, risk analysis, safe management, and then control of development, or land use planning, and emergency response. They are mitigation measures, basically. They're not really affecting the risk posed by the pipeline. What they're doing is saying, well, if it fails, we're controlling the consequences. Okay, land use planning controls the consequences because it prevents developments where people are going to be living and working. It prevents them being too close to the pipeline. And emergency response is a mitigation, because in the event that an accident happens, there'll be evacuation, etc. And then obviously, I'm sure most of you have heard of process safety and the principles of process safety. Guidance and good practice should always be applied. There are a number of references for safety management systems. The key one in the UK is the HSE's HSG 65 document, which basically breaks down the activities into the plan, do, check and act requirements, and the requirements for health and safety management and also for process safety are being picked up and are included in the pipeline standards. Let's just, for a minute, think about the relationship between legislation, risks being as low as practical, and codes and standards. The general process is this one. You start off with expert knowledge. So if you want to create a standard for something to make sure that it complies with legislation, you've got to start off with expert knowledge. And that expert knowledge needs to be written up as a standard, and then it's got to be reviewed by other experts, reviewed and agreed by other experts. Once that's happened, you've got good practice, and good practice then has to be turned into rules. Once you've got a rule, it goes straight into a code or a standard. Rules have got to be formulated in such a way that the reader or the user of the standard understands what the rule is and understands how to apply it. Once you've done that, you've established that risks are as low as reasonably practical, and that gives you compliance with legislation. So the point there really is it's an ongoing process. Unless you're absolutely sure that you know absolutely everything about the subject, you've got to keep doing this. And the problem with pipelines really is you're never going to be in that situation, because pipelines are long life assets and they're generally constructed on third-party land. So the environment around the pipeline is always going to change. So it's very difficult to say that you're always going to be in a position where you know exactly what is going to happen. Standards and codes basically have to apply throughout the life cycle of the pipeline, and the key ones that I'm going to talk about from now on are, in particular, GMT, which is very closely linked to 8010 Part 1 in the UK. Those standards are very much based on the American ASME standards. And then, of course, these standards are based on these standards, but they apply within Europe, so they've got to link with European standards. And then, of course, the ISO standards, which set the international baselines, they have got to be complied with also. ISO standards haven't got the history of the ASME standards, which is why all the background I'm going to talk about will explain how code standard thinking in the UK is linked to ASME, not ISO. That's not saying that the ISO standards shouldn't be applied, it's just saying the history with ISO standards wasn't there when all this process started. Right, so the aim of the standards, this is the aim of TD1, which is exactly the same as the aim of ASME. TD1 is the gas pipeline standard in the UK, and this aim is exactly the same as the aim of the ASME B31.8 standard for gas pipelines. So you've got to recognise the pipeline failure modes and consequences. You've got to minimise the effect of consequences of failure, and you've got to minimise the frequency of failure. So we'll look at how what's been done to do that. So TD1 was based on the American ASME standards, and the key development of the ASME standards started in the 40s and 50s in America. The main interest in the UK started in the 1960s, when the UK was building the national gas transmission system, really with the intention of using natural gas, which of course had already started in the US. So the Americans were experiencing a lot of material and fabrication problems, and the research programs in the UK, which were predominantly led in the UK at the time by the nationalised gas industry, so essentially they were government funded, They concentrated on failure assessment, materials testing, in particular avoidance of running fractures, which the Americans had had some experience of. Concentrating on pipe damage resistance and consequence analysis. That was particularly a UK concern because the UK is a much more densely populated area of land than most of the tracts in the US where the large pipelines were routed. So all of this was going on while the UK gas industry was starting to build the natural gas transmission system. And so they learned while they were actually building the system. One of the learning points was what we talked about earlier, where there was a failure of the pipeline at Yarm because the construction machinery hadn't been controlled on site and damaged the pipeline after it had been tested. The key design rules which were established, which are important because these were established during the research predominantly in the 1970s, but they still apply today. Design factor and wall thickness, proximity distances for occupied buildings in the vicinity of the pipeline, hydro test requirements, and fatigue. So the principles of TD1, let's think about routing and proximity, takes account of the characteristics of developments and patterns of population, minimises risk to the public, but most importantly recognises there is a finite possibility of failure, and the proximity distances are in place to limit consequences of failure. So the way it does this, it's based on the thinking in the ASME code. The ASME code actually defined a fixed corridor across the pipeline and then said you've got to control buildings within that corridor, and depending on the buildings that are there, you've got to change the design factor of the pipeline. That was, the principles were seen as being robust and needed to be applied, but they wanted to apply them differently in the UK. So they defined proximity distance as a multiple. They defined proximity distance based on the diameter and pressure of the pipeline, and then they defined the corridor over which that applied according to the pressure and diameter of the pipeline. So now you can see, instead of having a fixed corridor across the pipeline, you're going to have variable corridors depending on the diameter and pressure. You've then got to count buildings and numbers of people, and this is where if you can easily count buildings, you can't necessarily easily count numbers of people, but if you interrogate what the building's there for, you can decide, you can make a reasonable judgment as to how many people are going to be associated with it. So if you're doing quantified risk assessment in the UK, you assume that for every house you've got 3 persons in that dwelling, and that comes from the national census, which is carried out every 10 years. You classify the area basically depending on whether you've got a low number of people or a higher number of people. And if you're in a town or a T area, you can't build a high pressure hazardous pipeline in the UK. You can't route it through a town area. So let's just look at the principles of this. This is a standard pipeline routing design. So basically you've calculated your diameter and pressure, so you know what the corridor is of the pipeline, and you now roll that corridor down the route of the pipeline, and you identify where you've got buildings which probably mean you've got too many people close to the pipeline at that location, so you're going to have to change the design. So if the pipeline population density is less than or equal to 2.5 persons per hectare, it's classified as class 1 or rural, and you can operate up to a design factor of 0.72. If the population density is greater than 2.5 persons, it's a class 2 or a suburban area, and you've got to drop the design factor to 0.3. Now this is one of the areas where the UK codes are much more onerous than the ASME codes. The ASME codes start at 0.72 and they drop to 0.4, and they drop in stages, so it goes 0.72, 0.6, 0.5, 0.4. In the UK, you start at 0.72 and then you've got to drop straight down to 0.3. But we just think about how this works. So if you did the assessment I just talked about, you'd say, right, okay, wherever you're crossing a road or a railway line, you assume that you've got to have a 0.3 design factor. So you're going to have thick wall pipe there. Wherever you're passing developments where you have people in occupied buildings, you've got to drop the pipeline design factor, which means you've got to thicken the pipe up. Now, during the operation of the pipeline, one of the key issues, and I'm sure you'll do examples of this in your QRA lectures, one of the issues is once you've designed, installed and started operating the pipeline, somebody will come along and build something close to it. So straight away you're then not complying with the pipeline standard. So the risk might be unacceptable to the people associated with that development. So you've got to do a survey and identify exactly what's there. You've then got to do a risk analysis, which in this case must be a quantified risk analysis. And you've got to identify risk reduction methods, and you've got to do the ALARP assessment to say, well, do I actually need to apply these? Now, the proximity distance was based on a lot of research which was carried out in the UK and also in Europe during the 1970s and 80s in order to actually quantify the thermal radiation which would occur in the event of a fire following a major release. And this is actually developed in terms of proximity curves which are in the code, they're in the standard, and what you've got is the maximum operating pressure plotted against the minimum distance. So we're talking about a minimum distance, that is the distance which has to exist between the pipeline and any occupied building. And then the different curves are for different diameters of pipeline. So you can see that as the pipeline diameter goes up for the same pressure, the distance starts to increase. Now, it's important to realize that these distances are based on predictions to a thermal radiation level of 32 kilowatts per meter squared. That is not a safe level of radiation. So if you happen to be standing at the proximity distance and the pipeline ruptures and a fire occurs, you will not be safe at that distance. In our areas, the curves are based on a design factor of 0.72, and they go up to a maximum pressure of 100 bar. And they assume that the failure mode is rupture. So those curves are assuming you're going to have a big fire. In S areas, you've reduced the design factor to 0.3. You've still got a maximum pressure of up to 100 bar. But in this case, because you are modifying the design of the S area pipeline, so you're bringing the design factor down, and you are increasing the thickness of the pipe to do that. If the pipe wall is less than 9.5 millimeters, you assume that your consequences are going to be severance of a 6-inch diameter pipe. So essentially you've got a 6-inch hole in the pipe, 6-inch leak. If the wall thickness is greater than 9.5 millimeters, or you've got impact protection, you can bring the size of the hole down. So in this case you would assume a 3-inch hole. Where the wall thickness is greater than 11.9 millimeters, essentially the code says, well, if you've done everything right, you shouldn't have a consequence-based proximity distance, and you can allow buildings to go up to 3 meters within the pipeline. The wall thickness limits were obtained from research. This is a simplification of what research did, but what they did was to look at the effect of impact damage on the pipeline. And the criteria they applied was you're going to hit the pipeline with a sharp machine tooth, and if you produce a dent of 0.2 inches depth in different materials, then that's going to give you a limit on wall thickness. And basically wall thickness is here, that's the 9.5 and that's the 11.9, and they were related to the damage that could be caused by typical construction machinery. And one of the key issues, this particular machine, which I would probably recognise if I saw one, but I can't really tell you much about it. That machine is used a lot in agriculture to do activities like drainage. So there is a lot of possibility of damage using that sort of machinery. The design factor, I use this slide because this is the original research slide that was presented to the committee which was developing the standard. And what they did was they looked at essentially where you move from having a failure mode of a leak to a failure mode of a rupture. And the concern here was corrosion defect. So we're essentially plotting the length of the defect along the x-axis and the design factor along the y-axis. And what you can see here is that once you get to a design factor of around 0.3, you've got to have very long defects for those defects to rupture. So 0.3 was taken as the limit at which it is safe and reasonable to avoid ruptures in S-area pipelines. And a lot of this work then got consolidated through the NG18 equations, which allow you to predict the leak rupture behaviour of the pipeline. And essentially, if you're doing an integrity assessment of the pipeline, you need to be able to demonstrate that the damage that it will see is going to leak, not rupture. Right, these, again, these are old diagrams which were used to demonstrate this concept to the committee that was responsible for developing the code. So what we're looking at here is design factor plotted along the x-axis against a relative rupture frequency on the y-axis. And you can see after design factor of 0.3, the relative rupture frequency is very low. So that justifies that. In terms of wall thickness, we've got wall thickness plotted along the x-axis and the same relative rupture frequency plotted on the y-axis. Here you can see the 9.5 millimeter wall thickness. So there's a reasonable likelihood of rupture there, which is why the code will say, well, at that thickness, if you're not at a design factor of 0.3, you need to put protection in to avoid external interference. Here you've got the 11.9, which you can see, although the code is saying you can go down to a zero consequence proximity distance, you still have the likelihood of corrosion. So what was introduced then was what the code, or the standard TD1 calls proximity pipe. In other words, if you get to this level of wall thickness, you're not going to sustain damage which will rupture. And that's actually in the code. If you read the code, which you will because you're going to be doing an assignment with me, which will start. I can't remember if it started this Friday or next Friday, but you will be reading the code. You'll find that's 19.1. Right, so the principles of the code require that you apply fracture control during the design of the pipeline. And this means that basically you've got to ensure that the design and the toughness requirements of the material are such that you're going to have resistance to the initiation of small defects. In other words, if you've got small defects in the material, they're not going to grow under the operating conditions. If they do grow, you want to ensure that they're going to leak rather than rupture. And if they do rupture, you've got to make sure that they're going to arrest so you don't get a propagating fracture. And then absolutely essentially you've got to avoid brittle fracture and you've got to arrest ductile fracture. The reason you avoid brittle fracture, this is an old slide, an old research slide, which is taken down the axis of a failed brittle pipeline, and what you can see here are the brittle cracks. So you can see that basically that pipe is just going to absolutely fall to bits. Brittle cracks are very onerous because the speed at which they propagate is incredibly high. So basically 1 minute everything looks okay, the next minute it's in pieces. So it's very difficult to control. You avoid brittle fracture using a series of material tests which have got to demonstrate the material is adequate before you start using it to construct the pipeline. The typical one is the drop weight tear test, which is required for gas pipelines. And what that basically says is you've got to have either 75% or in some cases 80% shear area at 0 degrees centigrade. The problem with the drop weight tear test is it can really only properly be applied to pipelines which are 12-inch diameter and above. But it is very good at ensuring that if you do get a rupture, it's going to arrest as there and not propagate for extensive distances. However, because it's expensive and it can't easily be applied to pipelines less than 12-inch diameter, in many cases the Sharpie test is used here, and the Sharpie test really is used to ensure that at the design conditions of the pipeline you are operating on the upper shelf of the material. And they're just some pictures of typical Sharpie impact. Again, if there's any of you here who are interested in material properties, the issue we've got with Sharpie tests at the moment is that the pipe manufacturing methods now are so good that you, if you take Sharpies from them, you can't fail the Sharpies, which is an interesting concept, but it's not really telling you anything about how safe the material is. The test isn't working. So we need, for high quality pipe materials now, we need another QA test which is going to provide the level of assurance. And the level of assurance is that the Sharpie test doesn't actually fail is not really good enough. Right, now fatigue life of pipelines, the concept which is included in TD1, which again I'll be asking you to apply this concept in the assignment that we're going to start. What this is doing, first of all, there is an SN curve which is in there. Provided you have done a proper hydro test, you can apply that design, that fatigue design curve. And what the hydro test is you apply the high test pressure, which is high enough to ensure that any defects which survive that test are not going to grow to failure at the operating pressure during the pipeline life. Okay, and the failure is actually a defined number of cycles. So what, provided you apply the high level hydro test, what that means is you can use that SN curve, and you can apply 15,000 cycles of a stress of 125 newtons per millimeter squared, and that gives you a defined fatigue life. Right, there's a couple of diagrams in, and these are in the notes as well, which are basically just showing how the standards, how current standards are structured. Most standards start with a lot of emphasis on the route, safety, environmental and constructability, require you to follow quality assurance and the various safety, environmental management systems, and also the pipeline integrity management system. those principles are then applied to the design, material selection, and in all cases there's a lot of emphasis on control of corrosion, because steel pipes will always corrode. Always something will happen that will cause corrosion. So you've got to deal with that at the design stage and make sure you've got measures in place. Okay. This is probably, this slide is quite important. So please take it away and make sure you follow it, right? Basically what this is doing is saying, we've already said that standards have to apply through the life cycle of the pipeline. The life cycle of anything that you're applying a standard to. But in terms of pipelines, they start applying at the planning stage, which is where you're thinking about where you're going to put it and what you're going to do with it. They apply to the design and materials, construction, commissioning, operation, inspection and maintenance, and then at the end of life, either the revalidation or the decommissioning. And what I've done is shown in red how the standards are controlling damage, and if they're controlling damage, they're therefore also controlling the likely failure mode that you're going to get. What they're doing to control that all through the life of the pipeline. Okay, so if you do nothing after this lecture at all, please look at that diagram. And the other thing here is you're going to do you're going to study risk assessment in some detail. In fact, you may have already started it. The codes that apply, the ASME code and the UK codes that are based on the ASME code, are integrity-based codes. They're not risk-based codes. Okay. What that means is you can't just ignore the rules in the code and do a risk assessment and say it's okay. You can't do that. You've got to apply the code. However, they allow you to apply risk assessment as a decision tool if you're dealing with a situation, a typical situation during the life of the pipeline. You suddenly have a non-compliance situation because somebody's built something next to the pipeline which wasn't there when you installed the pipeline. So they allow risk assessment to make decisions in that sort of situation. And in some cases where the code is difficult to apply, difficult or very expensive to apply, like for example the code has got requirements in it for road crossings. If the highways authority or the local authority suddenly decides they're going to change the road over the pipeline, does that mean you've got to dig the pipeline up and relay it? Or does it mean you can consider doing something else? So they'll allow risk assessment in certain situations, but the codes are not risk-based codes, which means that the procedures that are embedded in the codes are influencing how damage might occur and what failures might occur. The types of risk assessment that you would do depend on why you're doing the risk assessment, and they also depend on what level of risk you're in. However, so I put this in because it's in the reference material, certainly on the HSE website, and it is very good guidance. What it's basically saying is you don't really start trying to quantify risk until you know you've got a problem. The problem you've got with pipelines is because they are generally on third-party land, and they can be, and people have got access to the land over them. In most cases, if you're going to do any sort of assessment of risk of pipelines, you generally go straight to the QRA level. The codes cover a number of management systems. The most important one is the safety management requirements, which are generally based on regulator requirements. In the UK, we use the health and safety executive requirements. In other parts of the world, regulators have published their own requirements. The safety management requirements are generally they're linked through formal quality assessments. For example, the quality assessment particularly applies during construction and testing, because if you don't do that right, the problems you leave are going to be there for the rest of the life of the pipeline. So the QA is very, very important in construction and testing. Environmental management is essential because environmental legislation is highly onerous, and if you do anything wrong, you'll get very severely penalised. But safety management is generally very closely linked to integrity management. That's taken straight out of the code, just to give you an idea of how these things are linked. And this particular diagram, which I would certainly recommend that you consider if you're doing any sort of integrity work, it's taken straight out of CME8021.8S, which is a very good integrity management standard, very extensive, it's got a lot of information in it, and the procedure that it applies is basically shown here, and the procedure is cyclic. So you start off by identifying potential threats, and you evaluate the risks. You then look at the control measures. You prepare an integrity management plan detailing all the activities that you've got to do to make sure that the control measures are in place. Then you apply implement the integrity management, and you then carry out reports, in particular surveillance, inspection and maintenance reports, in accordance with the plan. You compare those with the level of integrity you think you're actually controlling. To do that, you've got to review trends. So if you've got a process in place to control corrosion, you've got to look at your corrosion records and decide, are you controlling corrosion or are you not controlling corrosion? If everything's adequate, then you just keep going around that cycle. If you identify something which isn't adequate, and a typical example here, if we stick with corrosion, a typical example might be that suddenly you identify that you've got AC corrosion or DC corrosion on the pipeline. So something has changed in the environment and the controls are not adequate, so you've got to go through the cycle again and put in the controls. And there's no issue here, well, it wasn't there when I built the pipeline, so I don't need to do it because the code isn't retrospective. That doesn't apply. The code, in aspects like this, the codes are retrospective, and if the threat is identified, you must address it.
Excuse me. So what if you're trying to control a particular defect, and you actually notice that you've controlled the defect, but when you check the game like a surveillance, you notice another issue. So you keep doing this for the control one and start another one.
Absolutely, yes. So you've got to have something like this for all of your damage mechanisms. You've got to have all of your damage mechanisms picked up at the very first stop where you're identifying the potential threats. And that's why the publication of standard damage mechanisms is so important, because you need to start off with a checklist, and that checklist has got to reflect what other people have found. Okay. Right. There's a lot of interest in reassessment of design life or life extension at the moment, and this is the reason for this is because pipelines are generally seen as safe. They're long life assets, and so basically at some point you're going to say, well, did they have a design life? Certainly if you considered fatigue at any point, or fatigue or corrosion growth at any point, they will have a design life. And if you still want to operate them at the end of that design life, what do you have to do? So there's a number of procedures involved. There's an ISO standard which I've forgotten what it is at the moment, but it's being published, and it's very good in telling you what you should do. There's big gaps in how you do it because all of this stuff is actually very difficult. For example, if you look at the integrity of the pipeline, do you know everything about it? Do you know everything about the corrosion in the pipeline? Do you know everything about potential fatigue crack growth in the pipeline? And for things like fatigue, have you actually recorded all the historical cycles accurately enough to do a fatigue analysis? So there's quite a lot of difficulties here. Again, if any of you are looking for any areas of potential research project area, then this would be a good one. Right, so minimizing the frequency of pipeline failures. This is this slide. It would be a good idea to link this slide back to the one that I told you to pay attention to. Okay. So we're minimizing the frequency of pipeline failures by, first of all, avoiding material and construction defects, and that means we've got to have good technical specifications, and we've got to put on a good test of pipeline integrity before we commission pipeline. You've got to control degradation, which means you've got to have design and installation of good corrosion protection systems. You've got to ensure the pipe resistance is sufficient to resist the majority of likely damage, and that basically means you've got to have the right wall thickness and protection measures over the pipeline. And you've got to control the operating stress if you want to control the failure mode of the pipeline. And basically that means you've got to have a low design factor if you want to ensure that you're going to leak before rupture. And then if we think about minimizing the consequences of failure, the main issue in the codes here is the location selection, and that means you've got to route the pipeline and classify the area that it's passing through in terms of the development and population density of the pipeline. You've got to route wherever you can, you route through areas of minimum population and infrastructure, and there will always be hotspots that you can't avoid, so you've got to have the design approach right for there. And you've got to establish correctly the distance from population and infrastructure, and you've got to make sure that you maintain the minimum distance at all stages of the pipeline life, which means because you're not in control of the land around the pipeline, that means you've got to keep going and looking and checking what's there, and then if there's something there that doesn't comply with your design, you've got to do something about it. We ended the last lecture on the issues associated with intentional external interference, and the difficulties here are how do you actually capture this? At the moment, I'm saying it's not covered by legislation. It is really covered by legislation in the UK, because anybody who damages a pipeline is subject to is basically carrying out a criminal offence. But who is the responsible party? This is a bit of a difficult issue, because legislation normally places the responsibility on the party who is responsible for posing the risk, and the risk associated with pipelines is where it is and what's inside it and what might happen if you get a release. How can you normally need data to assess problems and to come up with good, robust solutions. But how do we get this data? Because all of thinking to date on control of external interference has always been based on the fact that external interference is a random event and it happens by accident. When people are doing it on purpose for a particular reason, we need new models. We need a new way of thinking about that. And while there's this is being considered by pipeline bodies like UCOPA and Concawi, it is being thought about, but it's not emerging. Again, if any of you are looking for project areas to pick up, this could well be something which would be good. How do you address the risk to the perpetrator? Because if somebody's deliberately tapping into a pipeline, an accident could occur and they may get severely hurt or killed in that event. So how do you deal with that risk? Does that mean you've got to make all pipelines capable of resisting intentional interference? what are the intended consequences? You've got to think about that because that will tell you what likelihood you've got to controlling it. If people are carrying external influence out because they think they're going to make lots of money, then it could be quite difficult to control it. If people are intentionally interfering with pipelines because they want to steal fuel because they're too poor to buy it, that is a different issue, and there should be different ways of dealing with that. And essentially, what are the unintended consequences of this? Most people who interfere with pipelines on purpose don't really fully understand what the consequences could be if that goes wrong. Right, well, you've been very patient and you haven't had a break. If you've got any questions, please ask them now. If you take anything away from this lecture at all, please take away failure modes, what causes the failure modes, what damage modes cause them, and how the codes control that. That's the key issues. Okay, has anybody got any questions? Okay, thank you very much.
Thank you.
Excuse me, ma'am. I want to ask a question that's been stopping my mind. From where I come from, your home gas supply is not, you don't have that kind of system in Nigeria. We just buy gas from a local gas supply.
All right.
So in the UK, I discovered that when you get to your kitchen, your gas is running into your kitchen.
Yeah.
That means there are some short or small diameter distribution
That's
lines.
absolutely right, yeah.
Okay, so what are the
Maintenance of...
measures that are put in place for these small diameter pipelines? Because
Right.
it's almost everywhere.
It is everywhere, and in the UK, the view is the major accidents that I've been talking about are generally low frequency. They have big consequences, but they're low frequency and you can control them. The danger and where you really kill people is where you take gas into their homes, and the pipes are very small, they're easily damaged. The appliances that they're connected to may not be working properly, so you've got a big issue. Now there's legislation. I mean, if you did a Google search on distribution, control of gas distribution pipes in the UK, you'll pick up legislation. I've forgotten what it's called at the moment, but if I looked, I would find it. And if you look at the TD3 design code, that covers the requirements for distribution systems. There's also distribution is the low pressure network, right? But then there are services connected to the distribution pipes which then take the gas into houses, and there are additional codes for services as well. And it's all to do with the materials you use, how you route them, how you do connections, and then how you go back and inspect them afterwards.
Really, some of the slides are not the same as what we have on the blackboard. Is that
No, a lot of the pictorial slides I use are for example, and I don't make them available on Blackboard because I have been taken to task for making them basically what happened a few years ago. A pressure group that was making complaints about a pipeline project took some of my slides and then went and displayed them all to the local. So I don't think you need the slides that I've shown. If you really wanted things, you could probably go onto the internet and look for stuff. But I don't put them on really for that reason.
even the slide just now when you say it was important to take note of, I don't think it's in the slides.
It should be.
It is.
Right now,
So I'm pretty we're talking about the one with the pipe life cycle, right?
Yes.
Yes, but we have the one without the words.
Right, that's because they're not up. What's the name of this file? 2016. I've given them a 2017 one.
Okay.
So, so the notes are available, and I did ask for them to be put up. The lady who was dealing with it said she might not get them up in time for this lecture, but they would be up this week.
Okay, yes. I'll look out for that.
Right, okay.
Thank you.
I just wanted to inquire about any job opportunities. Do you have any connections? If I could send you my CV, could you forward it to?
Yeah, I mean, by all means, send me your CV and I'll forward it. I work in a very small company.
I know you work in
so we don't really have staff working in the company. It's basically myself and my co-director, but we have got contacts, and if I can pass your CV on, I certainly will.
Well, that would be excellent. So I will do that today.
Right, okay. You need to use my personal email, not my university.
Is
Yeah?
Is it on your website, Piano?
Yes, it will be. Yes, so if you put the query, but basically it's jane.haswell@piuk.co.uk.
That one, yeah?
Yeah,
Yeah, then I will forward my CV today.
right.
Yeah, thank you very much.
Okay.
Is she still in this? I haven't seen any. Angel.
But there is there is no direct, no risk, but there is a direct flight. Yeah, but let's see. I oh shit, my phone is gone. No battery. Anyway, there are 3 weeks from training. Yeah. So I will bring it from. I will take a picture with it. And I found the cost to go to Kilimanjaro. It costs about 700 pounds. So you don't go to Kilimanjaro? No, you have to. From March 22nd, I'm leaving here. Yeah. London. scientists.